Hi everyone, welcome to the second to last unit, and we have one more to go after this, which would be probability, and yes, we have enough time to do that, so here we go. This unit is called Not Everything is at the Origin. Usually we do these graphs out by hand, and then we look at them on the graphing calculator, but obviously we won't be doing the graphing calculator piece, so lucky you, I guess. All right, so there are 4 graphs that you are responsible for, and we will be practicing them over the next couple of days. And we've seen all of them before, except, I guess 2. All right, so the first one we're looking at is absolute value. And what we call the parent function is basically the function written with the bare minimum. So the parent function of the absolute value function is just y equals the absolute value of x. There's nothing added or subtracted or multiplied by it. So the goal of these graphs that we're about to make, I know some of you just hate making graphs, and I'm sorry that we're back at it here, but the goal of these graphs are not to substitute numbers in to the equation that you're given. Rather, you use what's called transformations. So I should actually call this general transformation. I will obviously take pictures and post these on the classroom, but also I found a really nice PDF that I added to the notes section that includes this, so you could check that out. But so general transformation notes, what does that mean? It just means how do graphs of functions move around the plane? How are they different from the original parent function? So if we had something like y equals just negative x with no parenthesis, that means you flip the graph over the x-axis, which is the same as multiplying your y values by -1. If your new function is you have x plus some number c, that means you are moving c units to the left. Opposite of what we would think. Positive, we usually think right, but when it's in the parentheses of what's happening with the x, we go to the left c units. When it's in the parentheses with the x and it's x minus c, this is opposite. Minus c in this case means right c units. When there are no parentheses and it's just saying x plus c, you're going to go up c units. So in this case, positive means up. No parentheses, x minus c, negative means down c units. And the last type that we're going to look at in our class is if we had y equals k times x. That means you're taking your y values and you're multiplying them by k. It represents a vertical stretch or shrink depending on what k is. So if k is bigger than 1, it's a stretch, a vertical stretch, meaning the graph would become kind of skinnier. And if it's a vertical shrink, that's when, and I shouldn't have a C here, sorry. If k is between 0 and 1, vertically it kind of gets wider, I guess we'd say. All right, so you might be really confused because we haven't even done anything yet. So back to what's going on here. So our parent function is y equals the absolute value of x. And I don't want to remind you about what that looks like. You have the point 0, 0, 1, 1, because the absolute value of 1 is 1, and negative 1, 1, because the absolute value of negative 1 is 1. This is the one that looks like a V. Remember, absolute value, we said, is V. So this is Y. I'm actually going to rename the second one and call it G, just to be something different. I should say of X, I suppose. All right, so now our new function that I want you to graph, G of X equals negative 2 times the absolute value of x plus 3 minus 2. So remember, I do not want to see you having a table and substituting in values. Your goal is to figure out what does this negative 2, positive 3, and negative 2 mean. So this negative 2 on the end, it's not in the parentheses or anything with the x, so it's this one here. It's whatever's happening to the x, and you're subtracting c. So that really means you're going down 2. This plus 3, that's in with the x. Whatever's happening to the x, we have a plus 3. So that means we're going to go left 3 units. Left 3. This negative out front means that you're going to flip it over the x-axis or multiply your y's by -1. So flip over the x-axis. And then this 2 on the outside, this is like right here, y equals kx. You're multiplying your y times your k, and because 2 is bigger than 1, this is a vertical stretch. So if you write little notes to yourself, this is kind of what I want to see. I don't just want to see a final answer, I want to see you doing out these graphs. So one strategy you can use is to take the original 3 points that I have here from the parent function, and I'm going to move each point to get to my final graph. Gonna put on some tick marks here. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so which transformation should you do first? Well, I always tell people to kind of work left to right, deal with the multiplication first. So I'm going to take these points, flipping over the x-axis, and do a vertical stretch. So let me show you the flip over the x-axis. So if I flip this over the x-axis, -1, 1, that's going to reflect to here. 0, 0 isn't going to go anywhere. And 1, 1 will reflect to 1, -1. So I did that. I might do this in colors to kind of show you the different moves. Okay, vertical stretch. That just means you're going to take these y values and multiply them by 2. So I'm at -1. That's my y value. I have to multiply that by 2. So I'm going to end up at -2. Same deal here. The y value is -1 times 2 is -2. The y value here is 0, and 0 times 2 is still 0. So I did that. Again, some of you might be able to do this in a couple of steps, but I'm just showing out every single scenario here. Now I need to take all those points and move them left 3. Okay, so I'm at, my last one was the green, so I'm going left 3. 1, 2, 3. Okay. 0, 0 has to move. 1, 2, 3. And then this guy has to move 3. 1, 2, 3. Okay, there's my pink. Alright, and the last movement is I have to go down 2. Okay, so I'm going to go down 2. I always work left to right, so I'm going to go down 2. I wish I had graph paper. Should have grabbed some of that when I was at school. Not thinking. Alright, so down 2. This point moved down 2. And this point, 1, 2. It should be even Stevens here. So, oh, lovely pen. Alright, so I want you to label. I'm just really striking out here. It's hilarious. I want you to label your final 3 points and your graph. So this is g of x. And so this is the point 1, 2, 3, 4. So this is -4, 1, 2, 3, 4. This is the point -2, -4. And this is the point -1, 2, 3, -1. Just want you to label that somewhere. I will do one that's maybe less involved here just for a second. I'll call it 1A. So if I asked you to graph k of x equals the, negative absolute value of x plus 1 minus, we'll do plus, I guess, 2. Alright, so here's quick movements. 2, 3, 4, 5. Okay. Alright, so I always use my parent function graphs, those 3 points, and I move them one at a time. So this, again, what does this mean? I'm going to flip over the x-axis. I'm going to go left 1, and I'm going to go up 2. Alright, so here we go. I'm going to take this point, I'm going to flip it over the x-axis. I'm then going to go left 1, and then up 2. 1, 2. So that's the point, -2, 1. 0, 0. Can't flip it. Oh good, I'm not focused. I go left 1, and then I go up 2. 1, 2. This is the point, -1, 2. Last point. I have to flip it over the x-axis so it becomes at -1. I have to go left 1, and then I have to go up 2, 1, 2. So this is the point 0, 1. And there is my final graph. And that would be sufficient work. If I can see when you take a picture of your work, you know, your counting points, something of that nature. So that's our video for absolute value. I'm going to break these up, so if you need to go back and rewatch a certain type, you can do that.